Good, good evening, everyone. Celso Batalha Choten, and today is Monday, and we are pretty much focusing on star or stellar evolution. And this website, aspire.cosmic-ray.org, they have some good materials and pretty much put together some of the terms that I asked you to create a composition and send it to me, and that is part of the discussion, which, by the way, is going to be closing tonight. I was able to read some of your comments by Friday. I didn't have a chance to go over the weekend, and I was able to reply to some of you by Friday, so I don't know what's going on right now, but I will check it tomorrow morning and see what you wrote. But basically, the main point in stellar evolution is to realize that stars are formed out of gas and dust that exists in the interstellar medium, and what you're seeing in this picture up here, these are clouds that might harbor star formation process. So in regions of these clouds, and they are very thin, the density is not great enough. It cannot even be compared with the density of our atmosphere, which is much thicker. So we are talking about few atoms per cubic meter. Few atoms, just to give an idea of how thin and how light these clouds are. But in certain locales, in certain locations, the density is good enough that gravity can initiate a process of contraction. And then slowly but surely, gas will be brought in towards the center of gravity or center of mass where a star is going to be formed. So the point of this webpage is to probably put together a few terms that you need to include in your composition. So to begin with, once contraction takes place, the time that it takes for that protostar or for that mature star to complete its evolutionary cycle. So it depends on the amount of material that has been brought in to this core. So which means more massive stars will evolve faster than low mass stars. And this was one of the points that I wanted you to emphasize in your discussion last week. So mass is the driving characteristics, is the driving quantity that controls stellar evolution. Hey, Kirtana, how are you doing? Good to see you. By the way, this is being taped, so I'm taping this lecture now. I don't know if you can hear me. I can see you, now I can't. So mass is the...
Yeah, I can hear you.
Oh, you're there? Okay. Yeah. So I'm taping this and I'm uploading to Canvas later. But basically, mass is the driving parameter that controls stellar evolution. So if we are talking about low mass stars as well as intermediate or high mass stars, they all go through their so-called protostellar phase. So a protostellar is a phase in a star in which gas that happen to be in the interstellar medium is brought to a center part where eventually a star will be formed. So again, more massive stars go through that process of contraction much faster than low mass star. A star like the Sun will take about 10 million years to complete its evolutionary cycle, and whereas intermediate or high mass star takes less time to complete that. Now, once this contraction takes place, the core itself, and this there is a phase that is not the main sequence, but is the so-called pre-main sequence phase. And let me see if I can find here. So a pre-main sequence star is one, I don't think I have it here. Get out of there. A pre-main sequence star is the one that last week, let me see if I can find it here, just a second. Wait a second. There you go. So we saw these figures last week. A pre-main sequence stars is one that eventually it goes to the phase of slowly contraction to the point that eventually becomes a main sequence. The definition of a main sequence star is one that is harboring fusion reactions in its very core. So fusion reactions produce the energy by gamma rays production that is the one responsible for keeping the star in hydrostatic equilibrium for a long time and for the most of its lifetime as a main sequence star. So the fusion of hydrogen in its core, converting 4 atoms of hydrogen into 1 atom of helium produces gamma rays and neutrinos. Neutrinoscapes do not interact with the solar interior part, neither interact with Earth. So we have 100 billions of neutrinos crossing every square inch of our body every second. We don't feel that because the interaction is much less. But the radiation, the gamma rays that is produced in the core, that energy is spread out, is transferred to the solar interior, is the one that keeps the sun stable in hydrostatic equilibrium. So since the sun was formed at about 4.5 billion years ago, initially the percentage of hydrogen and helium was pretty much the same as it is in the interstellar medium, 75% or so of hydrogen per mass and 25% or so of helium per mass, and trace amount of everybody else, all the other metals. But in the core, since hydrogen is being converted into helium, right now we found ourselves with our sun over 60% of helium in the core. So eventually the sun will be complete its evolutionary sequence when the core itself is filled with helium. And when this happens, there is no more fusion reactions going on in the core, right? When the core is 100% helium, and helium is the ashes of hydrogen burning phase, then eventually the core will slightly contract. And as we learned in previous or last week, as gas contracts, it heats up, the temperature goes up, but there is no fusion reactions because to fuse helium is required a much higher temperature, which is about 100 million Kelvin according to calculations. So in the case of a low mass star like the sun, the core will contract slowly as a result of this lack of fusion reaction. And what happened in the following stage is that surrounding the core, it will be formed a shell where fusion reactions will take place. So there will be fusion reactions of hydrogen into helium, but not in the core itself, in a shell surrounding the core. So while the core contracts and heats up, the shell produces fusion reactions. So the amount of energy coming out of the system core plus the shell outshines or is more important than the energy that was previously produced as a result of fusion reactions of hydrogen and helium during or when the star was a main sequence star. So the main result is while the core contracts, the outer layer expands as a result of this excess of energy that comes out of the core and core shell system. And as the star expands, because of this excess of energy coming out of the core shell system, the outer layers expands. So the collision between molecules and atoms and the plasma itself in the outer shell or outer layers in the atmosphere diminishes, and the star becomes less subjected to collision of its elements, which means collision in physics means temperature. So when you have less collision, the temperature is less. So the outer layers, the surface, the star surface expands and cools down. And as we learn in Wien's law, as the temperature goes down or falls down, the star becomes red, right? Less temperature, the star is red. More temperature, the star is blue. So the star expands, becomes bigger, and because it's cooler now, it's called a red giant. So the post-evolutionary main sequence phases is one in which the core is contracting, heating up. There is a fusion reaction going on in the shell surrounding the core, and the outer layers expands and cool down. And then we have these two effects going on at the same time. Core contraction heats up, outer layer expands, cools down. And visually speaking, we see the system as a red giant system or a red giant star.
Professor Taha?
Yes.
I was actually going to ask, I'm still a little fuzzy on Wien's law, so could you explain that one more time?
Yes. So can you hear me well?
Yeah, I can.
Yeah. So the core. Let me see if I can annotate here. I don't think I can annotate. So the core of the star, in a main sequence phase, you have fusion reactions going on. You have pretty much hydrogen fusing to helium and producing gamma rays. So are we all okay there?
Yeah.
Okay.
Yeah.
So, but eventually the fusion is gone because hydrogen is gone. Okay. So when the fusion is gone because hydrogen is gone, you have a core of helium. Now you have the star above the core pressing down on it. So all the weight of the star is now exerted on the core, which forces the core into contraction. Are we all there?
Yeah.
Okay. So as the core contracts, what happened with the gas in there? Becomes more dense, right? So
yeah.
the density, which means the volume diminished, the mass is the same. So if the volume diminishes, the mass is the same, the density goes up. So if the density goes up, the temperature of the gas also increases. So you have a core that goes from 20 million Kelvin. Slowly the temperature starts raising up, and it's going to go up to 100 million Kelvin, where the conditions will be such that helium can initiate and ignite fusion reactions. But during that time, the core is contracting, heats up. It's not at 100 million Kelvin yet. It is just as if you think as a black body, is just radiating more energy from it because it's hotter now, although the volume is less because it's reducing. But at the same time, you have a shell that surrounds the core, and in that shell, fusion reaction is taking place. You have hydrogen being fused into helium as it happened during the main sequence in the core, but now it's in the shell that surrounds the core. And when you budget the amount of energy coming out of these fusion reactions in the shell, plus the energy, the intensity of the energy coming out of the core, think about a black body with a temperature that is increasing. So when you add up those two sources of energy, the amount of energy that comes out of that system is more or is bigger than you had when the star was in the main sequence. So this excess of energy is able to overcome the weight of the star, the gravity force of these layers that surrounding the core all the way to the atmosphere. So since this outward pressure or the force that arises from this outward pressure overcomes the weight of the star expands. So we have a break in the hydrostatic equilibrium again, and then the star is pretty much expanding. But as the star expands, if you look in the outer layer, which is the atmosphere, the separation between molecules or atoms or plasma itself diminish. Because now, with the star expanding, the shell, which we call atmosphere, the outer one, it have less collision, becomes cooler. And because it's cooler, in astrophysics, we translate that into color. So cooler means red. So the star is expanded, which means a giant, and is red. Does that make sense?
Okay. Yeah, it does. Thank you.
So, so this process of core contraction and outer layer expanding, it goes on to the point that eventually fusion reactions take place in the core again, where helium is slowly fused into carbon and oxygen. So now the star, if you're thinking about a low mass star, is harboring fusion reactions again in the core, but it's not hydrogen and helium, but it's helium and carbon, basically. So this, we go to the p chain. And we are pretty much here. So if you look at an HR diagram, Hertzsprung-Russell diagram, here's a main sequence star, low mass one. Can you see my pointer? Right here?
Yeah, I can.
Yeah. So eventually, now the core fusion reactions is hot. It's not there anymore. The core contracts, the outer layer expands, and go to the point that eventually fusion reactions take place in the core again for a second time. At this time, it's not hydrogen and helium, but it's helium into carbon. Now, when these fusion reactions again initiated in the core, the star becomes sort of stable again, because now there is a constant flow of energy from the core. The core is not contracting or expanding anymore. It's pretty much stable, and slowly this helium is being converted into carbon with a outflow of energy that's pretty much stable, which leads the star to be what we call a horizontal branch star. So the horizontal branch star, it lies between the point where helium fusion reactions take place and the point where now the core is a core of helium atoms only, where the total amount of helium existing in the core is pretty much gone. So when helium was the ashes of hydrogen fusion, in a second stage, carbon becomes the ashes of helium fusion. So once the helium is completely exhausted in the core, now the core is a core of carbon. And the same process repeats. So the carbon at 100 million Kelvin cannot be fused into heavier atoms like neon, magnesium, or silicon. It doesn't do it. And so what happened is the core starts contracting slowly as it happened before, except that now this carbon core that is contracting goes from 100 million Kelvin and it starts to increase its temperature, right? So in this phase, as the book explains, the core, the carbon core, becomes surrounded by a shell where hydrogen fusion reactions taking place, and also a shell where helium fusion reactions is taking place. So we have these two shells where different types of fusion reactions happening because you have high density in these regions, but also high temperature. So for a low mass star, one that is less than 8 solar mass, that's it. So the material that's surrounding core and shells fusions is not enough to provide the needed density to ignite carbon fusion reactions. And the star cannot operate fusion reactions in the core anymore. So for a low mass star, and that's the point of today's discussion, for a low mass star, that's it. The carbon core is pretty much done. The shells switching in and off with fusion reactions eventually produces flashes that outcast the gas surrounding the shell onto the interstellar medium, and we call this type of system a planetary star. So a planetary, let's see if I can get here. In fact, planetary. Yeah, I don't have them here. Let me see if I can get some pictures as I did last year. Just a second. Let's see pictures of planetary nebula. So that is the situation for a star like a low mass star. Is the end of their evolutionary process. Is one that a core of carbon, which is, it has a name of it, is white dwarf. So a core of carbon, which is named white dwarf, lies in the center of the system, and the star that surrounded, or the material surrounding that core, is slowly spread out and cast off onto the interstellar medium as a result of flashes that occur near the core. And then you see these episodes of ejection giving different sort of configurations. So you have an hourglass configurations, as you can see here, probably here too, probably there too. You see just this spherical expansion like in ring nebula, or some more complicated morphology like you can see here. And all these different configurations is due to the type of magnetic morphology surrounding the star. So the magnetic field lines can trap gas in such a way, creating these different sort of morphologies that you observe in this picture. But planetary nebula are fantastic. They're beautiful system out in space, not these ones. And of course, these colors are all fake, and they are there just to highlight different features and processes in this overlying gas. But basically, in the center of this planetary nebula, there is a white dwarf right there. A white dwarf. You can see them quite clearly. See that little dot? You can see over there. Here is quite clear there. And that is a degenerate core of carbon star, basically. It's kind of a diamond the size of our planet Earth. That's the size of a white dwarf, which is a carbon structure completely crunched and degenerated. Okay. So the evolutionary steps of a low mass star, and that was part of the composition I want you guys to do, it leads exactly to this different process. So eventually the star expands when the carbon core contracts. The outer layer expands even more as a result of these double fusion reactions going on in one shell, hydrogen and helium, in another shell, helium and carbon. And this excess of energy expands the star much more than in the previous phase, and we call that expanding phase asymptotic giant branch, or AGB star. AGB star stands for asymptotic giant branch star. So eventually, the expansion is such, these outer layers are expelled, and then we have a planetary nebula. Eventually, all this gas surrounding the white dwarf core becomes mixed with the interstellar medium, and then we are left with a white dwarf. And as time goes by, this white dwarf core cools down and becomes a dark dwarf. And that is supposed to be the end of this type of stars. Now, if a white dwarf, or if that core, or if that star is part of a binary system consisting of another main sequence star, a low mass main sequence star, so you ended up with one of the core being a white dwarf, and the secondary star eventually goes through the evolutionary process as the white dwarf, right? Which now is a white dwarf. And eventually this secondary star expands to become a red giant, right? Like the other one. And when this happens, material might be able to reach the so-called Rush lobe, where gravitational pull of the white dwarf will efficiently drag material into the white dwarf. So when this happens, something interesting comes up, and that is, well, white dwarf have a limit to which material can fall on them. White dwarfs cannot be more massive than 1.4 solar masses, because when this happens, the entire star becomes unstable and explodes. So you have a 1.4 solar mass star exploding, and that the amount of energy that comes out of this explosion, if you think about the Einstein formulation mc squared, which is the amount of energy released by this material, so that energy can be picked even in exploding supernova. They are very far away. So astronomers, by observing this exploding star supernova type 1 and using the inverse square law, they can then pin down the distance to these events. And that's how astronomers in the last 20 years have been able to determine distance to galaxies that are very far away, but they are undergoing these explosive events. So here is the Chandrasekhar limit, 1.4 solar mass. So white dwarfs cannot be more massive than those this threshold. And if mass transfer is occurring as a result of a binary system, then the white dwarf, kaboom, explodes. And then if we happen to observe this type of explosion, and the amount of energy is equivalent to, think about it, 10 billion suns, 10 billion stars. And sometimes this explosion is so luminous that can outshine an entire galaxy. So galaxies that sometimes are fuzzy pictures in a sky map, they can outshine the entire region because of these exploding events. And if astronomers can detect that, they can, with very good certainty, because we know about the inverse square law, we can determine distance to these stars. What this inverse square law tells us is that the brightness of an event is equivalent to the luminosity divided by 4 pi distance squared. B is equal L divided by 4 pi d squared. Right? So the brightness of a system you observe with your telescope, you can translate what you observe to a certain amount of energy you receive down here on Earth. The luminosity is 1.4 solar mass, 10 billion suns energy. So you know that because they start to explode. And then, so you have two quantities in an equation that has three quantities, right? Brightness, you observe. Luminosity, you know, because of Einstein 1.4 mc squared and 1.4 mass that has been exploded. And since you know 2, you can determine the distance to that source. So I'm gonna stop taping this and I upload to Canvas. Just a second.